When this is section 5.7, in this section our goal here is to be able to classify the zeros of polynomial functions. We have that the fundamental theorem of algebra is the number of zeros of a function is equal to its highest exponent. So the degree of a polynomial is the number of zeros of that function. Okay, a repeated solution is a solution that is found twice in the same function. So for example here, x squared plus 6x plus 9, it factored down to x plus 3 times itself, x plus 3, which is the same thing as x plus 3 squared. Okay, therefore -3 and -3 are both zeros of that polynomial or function there. So there's two, they're just repeated twice. So for example here, we're going to go through these polynomials and see how many solutions does the equation have. Well, remember, the fundamental theorem of algebra said the number of zeros of a function is equal to the highest exponent that there is. So the degree in A is 3. It's coming from our degree here. So at most, there's 3 solutions. And in B, our degree is 4, so there is at most 4 solutions, or 4 zeros. Okay. In example 2, we're going to try to find all the zeros of that function. Okay, so first off, I want to do my P and Q. Remember, P is my constant, the factors of it, 7 and 14, because of my constant 14. Now I'm going to look at my Q's. My factors of 1 are just 1. So my P over Q's are the possible solutions are positive or negative 1, 2, 7, and 14. And again, we're going to try to test these out. I'm going to start with testing x plus 1. Okay, and again, we're going to do this with polynomial synthetic division. So I'm going to have the opposite sign of x plus 1 out to the left of my L chart. And my exponents are going in from biggest to smallest order, but I'm missing my x to the, or I'm not missing anything in this one. So I can go ahead and just write out my coefficients of my polynomial here. So that is 1, -4, 4, 10, -13, and -14. Okay, so I'm going to drop down the 1. So I got -1 here, -4 times, or plus -1 is -5, and when I multiply those, it gets positive 5, which makes 9, and here's -9, makes positive 1. 1 times -1 is -1 here, and -13 minus 1 more is -14, and that makes positive 14, which makes 0. So since we have 0 here, that tells me that this is a factor of my polynomial. And remember, this is the constant term, the x squared, x to the 3rd power, and x to the 4th power. So again, if I look here at my resulting polynomial, that'd be x to the 4th minus 5x 3rd plus 9x squared plus x minus 14. If I do my p's and q's there again, I'll notice that I can have plus or minus 1 as another solution. So what I'm going to do here is I'm going to test out x plus 1 again on this new polynomial. So -1 here, I'm going to flip the sign, and coming from up here, I have 1, -5, 9, 1, and -14. And again, I'm going to drop down that 1 and multiply. Okay, and 9 and 6 make 15, and then that's going to be a -14, which makes positive 14, which makes 0. So again, x plus 1 is another factor of the original polynomial, because whatever is a factor of that polynomial is also another factor of the original polynomial. So again, here's my constant, my x term, x squared, and x to the third power. Okay? And so now I know that I have a x plus 1 and an x plus 1 is a factor in my original polynomial, or it's repeated twice. Okay? So now if I look at this resulting polynomial, x to the third minus 6x squared plus 15x minus 14, if I look at my p's out of q's out of that, okay, I have plus or minus 1, 2, 7, and 14 again. Let me try to test a x minus 2, or it'll be 2 when I flip that sign. And again, I'm going to use this polynomial here. So x to the third power minus 6x squared plus 15x minus 14. Okay. And I wrote it all the way out, but I'm going to use the coefficients. Sorry about that. So 1, negative 6, negative 15, negative 14. So drop that 1 down, makes that 1 times 2 is 2. Excuse me, negative 4, negative 8. And negative 15 plus negative 8 is negative 23. And screwed up somewhere, let's see. Oops, that should be a positive 15. Here we go. There we go. Here's negative 8, and 15 minus 8 is 7. 7 times 2 is 14, and here we go, 0. So again, that's good. That tells me x minus 2 is now a factor. Okay, and here's what I got left. My constant, my x, and my x squared term. So what this tells me is, right now I have my factors are x plus 1 and x plus 1. They were repeated. And then we just found out x minus 2 was a factor, and we're left with x squared minus 4x plus 7. And now we got to see if x squared minus 4x plus 7 can factor all the way down completely. Well, we can't use the x method to factor because it won't work out. It's not factorable. So we have to use the quadratic formula on that. Okay, so with that, our a is 1. Our b is negative 4, and our c is 7. Okay, so when we do that, I have 4 plus or minus negative 4 squared minus 4 times 1 times 7 all over 2, because 2 times 1, or 2 times a is 2. Then I have 4 plus or minus the square root, negative 4 squared is 16, and 16 minus 28, because 4 times 7 is 28, is negative 12 all over 2. And that square root of negative 12 factors out to be 2 square root of 3i all over 2, which is the same thing as 2 plus or minus square root of 3i. And when I actually put that together there, I have the positive case of 2 plus square root of 3i, or this 2 minus square root of 3i. So with my factors here, I'm dropping down x plus 1 times x plus 1, that was repeated twice, x minus 2. Then I'm going to have x minus 2 plus square root of 3i. And then my other factor is x minus 2 minus square root of 3i. Okay, and here's going to be our zeros here. Set each one equal to 0, each factor. So I have 2 x plus 1s here. So x plus 1 equals 0. If I move this 1 to the other side, x will be negative 1. So I have 2 of those. then x minus 2 equals 0. I'll have x to be 2. And then if I set x minus 2 plus square root of 3i equals 0, okay, x is just going to be 2 plus square root of 3i, okay, and the other one, the last one, x minus 2 minus square root of 3i equals 0. That's just going to be x equals 2 plus square root of 3, or 2 minus, 2 minus square root of 3i. So I have 1, 2, 3, 4, 5 solutions, or 5 zeros of that original polynomial, which makes sense because my degree is 5 and it has at most that same amount of solutions or zeros there. So that is 5 zeros. Okay, we're going to do this next one. Same thing, I'm going to take out p, which is my factors of my constant, which is plus or minus 1, 2, 3, and 6. And then my q is plus or minus 1. So that means my p or q's are my possible roots or possible zeros are positive, negative 1, 2, 3, and 6. Okay, now I'm going to do the same thing. I'm going to test some x values out of here. Let me test, let's say, x minus 1. That means that if I switch a sign, it'll be positive 1. Okay, and before I do coefficients, let me go make sure that I have all my exponents from biggest to smallest. It goes 5, 4, 2, 1, 0. But I'm missing the x to the third term, so I need a placeholder smiley face 0. Okay, so I'm going to do 1 as a coefficient, negative 2, placeholder 8, negative 13, and 6. Okay, so drop down the 1. That gives me 1. Negative 2 plus 1 is negative 1. And 0 plus negative 1 is negative 1. And again, I have a negative 1, which makes 7. 7 times 1 is 7, which makes negative 6. And here's another negative 6, which makes 0. So that is good. So again, here's my constant, x term, x squared, x to the third, x to the fourth. And again, looking at that polynomial, if I do my p's and q's again, I'm going to have the same thing again here, where I can use or test x minus 1 again as a factor. So again, text x minus 1, so I'm going to have 1 on the outside. But I'm going to use this new polynomial here with the coefficients 1, negative 1, negative 1, 7, and negative 6. So I'm redoing that polynomial there. Because if it has a factor of that, it will have the same factor as the original polynomial. So when I drop down that 1, I have 1 times 1 is 1, which makes 0. It makes 0 again, which is negative 1. And 7 plus negative 1 is 6. And when I add that to negative 6, it makes 0, so that's good. X minus 1 is again another factor of the original polynomial. So I have the constant, the x term, the x squared term, and the x to the third term. Okay, so again, that means x minus 1 is repeated twice for this polynomial when factored. And now what I want to do is, if I look at this new resulting polynomial here, x to the third minus x plus 6, if I look at this p's and q's, it's still going to have the same possible factors, 1, 2, 3, and 6, the positive, negative cases. So let me try to test, let's say, test x minus 2, which means 2 will be on the outside. And now I'm going to test with those same coefficients, 1, 0, negative 1, and 6 coming from here. I'm going to drop down that 1. 2 times 1 is 2. When 4 plus negative 1 is negative or positive 3. 3 times 2 is 6. Okay. And I screwed up a little bit somewhere. Let's see. Oops, I should test probably. Since that one didn't work out, I would get 12. I need to go back and switch to x plus 2, which makes this a negative 2. And which is this a negative 2. Okay, and 3 times negative 2 is negative 6, which makes that a 0. So I'm going to test x plus 2, or use x plus 2 as a factor. And when I switch a sign, I need to use x minus 2 on the outside, or a minus 2. So since that came out 0, here is my constant, my x term, and my x squared term. Okay, so what this told me was this resulting polynomial has a factor of x minus 1, not plus 1, minus 1, and it was repeated again. So it has a total factor of x minus 1 twice. Then my other factor was x plus 2, and my other factor here was x squared minus 2x plus 3. That came from right here. Okay, so now I got to see, can x squared minus 2x plus 3 be factored all the way down? Well, I can't use the x method because it will not work. It will not be factorable. But again, I'm going to use the quadratic formula because that'll help me out too. So using the quadratic formula out of here, my a is 1, my b is negative 2, and my c is 3. So when I plug these in, I got 2 plus or minus the square root of negative 2 squared minus 4 times 1 times 3, which was c. That is a 3. So 3 all over 2 times 1, which was 2. So now I have 2 plus or minus negative 2 squared is 4, and 4 minus 12, because 4 times 1 is 3, is 12. 4 minus 12 is negative 8 all over 2, which simplifies down to 2 plus or minus 2 root 2i all over 2, which is the same thing as 1 plus or minus root 2i. Okay, so this told me x minus 1, x minus 1, x plus 2. This one is going to be x minus 1 plus square root of 2i. And the last factor there is x minus 1 minus square root of 2i. And again, we want the zeros. Okay, that's just factored down completely. So I'm going to have each factor set equal to 0. So I got x to be 1. And since I have 2 of them, I have 2 1s. Then I need x plus 2 equals 0. And when I move that over, x will be negative 2. Then this polynomial, or this factor here, x minus 1 plus the square root of 2i equals 0. When I move that over, x will just be 1 plus square root of 2i. And then my last one here, x minus 1 minus square root of 2i equals 0. X will be 1 minus square root of 2i. So I have 1, 2, 3, 4, 5 zeros. And that makes sense because my degree was 5, so at most I have 5 zeros for that polynomial there. Okay. So, some key concepts here. The complex conjugates theorem. If a plus bi is an imaginary zero of the polynomial f, then a minus bi is also a zero of f. So the first thing we're going to do is write a polynomial function, f, of least degree that has rational coefficients, a leading coefficient of 1, and 3, 2, and negative 4 as zeros. Okay, so we're actually going to write the function ourselves, given the factors, given the zeros already. So what we could do, knowing that these are zeros, is write them in factored form. So if I write 1 as a 0 in factored form, or factor form, that would be x minus 1. 3 would be x minus 3. 2 would be x minus 2. And then x plus 4. Oops, only 3, 2, and negative 4 is 0, so I can get rid of that. First one, x minus 1. It's just saying we need a low leading coefficient of 1. Okay, so now all I need to do is just factor these out to make a polynomial function f. Okay, so when I multiply these out, I'm going to start with the first two here. I'm going to start with x squared minus 2x minus 3x plus 6, and still multiplied by the x plus 4. So I got x squared minus 5x plus 6 times x plus 4. And now we can distribute that x to everything. So we're going to get x to the third power minus 5x squared plus 6x. And then the 4 to everything would be 4x squared minus 20x plus 24. And all we need to do now is put together our like terms. Well, x to the third power is not doing anything. And I have two like terms of the x squared, so negative 5 plus 4 is negative 1 x squared. Then I have my x term, 6 minus 20 is negative 14x, and then I could just drop down my constant 24. So here's this polynomial that when factored all the way down completely will have x values or zeros of 3, 2, and negative 4. Okay. So now we're going to write a polynomial function f of least degree that has rational coefficients, a leading coefficient of 1 and 3 and 2 plus square root of 5 as zeros. So here are going to be my zeros here. So if I write that as a factored form, that is x minus 3, if I want 3 to be a 0. And then I need x minus 2 plus square root of 5. And according to the complex conjugate theorem, the conjugate's also in here too as a factor. So x minus 2 minus square root of 5 as a factor there too. So what I'm going to do first is leave that factor x minus 3 alone. And I'm going to deal with the next two factors. When I multiply those, okay, I'm just going to kind of like group them together. So this would be grouped x minus 2 plus square root of 5. And then again, x minus 2 minus square root of 5. And if I go to FOIL that, okay, I'm just going to be left with x minus 2 squared and square root of 5 times the negative square root of 5, okay? That's like saying this, which is just left with negative 5. Okay, so now I can expand that x minus 2 squared, right? So x minus 2 times x minus 2. If I FOIL that, I get x squared minus 2x plus 4, which is the same thing as x squared minus 4x plus 4. So x squared minus 4x plus 4, and then I have that minus 5 there too. So I got x minus 3, and then I have x squared minus 4x minus 1. It's kind of like now what we did in the other one. Now we need to distribute everything to finish it out. So now I have x to the third power minus 4x squared minus x. And then if I do the other way, negative 3x squared plus 12x plus 3. And now all I need to do is put my like terms together. So f of x is going to equal, I don't have any other x to the third powers. If I combine my x squared terms, I get negative 4 plus negative 3 is negative 7x squared. Then if I do negative x plus 12 is negative or positive 11x. and then I bring down my constant of 3. So here's my polynomial here that will have 3 factors, 3, 2 plus square root of 5, and 2 minus square root of 5 here. And the last thing we're going to talk about is how we can use Descartes' rule of signs. So if a polynomial f of x is a polynomial with real coefficients, then the number of positive real zeros is equal to the number of variations in sign of f of x, or less than that number by some even number. And the number of negative real zeros is the same as the number of variations in the sign of f of negative x, or less than that number by some even number. Okay, so let's try to figure out how many positive, negative, or imaginary zeros there are for this polynomial here. Okay, so if I want to think of the positive zeros, it said just for f of x, we're going to look at just a normal polynomial in here and keep track of how many sign changes there were. So it went from positive to negative, to positive to negative, to negative to negative to negative. Okay, so I went from 1 to 2 to 3 sign changes. Okay, if I look at the negative side, I'm making all my x's negative now. So what that means is, basically, if you have an even exponent, the sign's going to change or stay the same. Okay, if you have an odd exponent, your sign's going to change. So if I go ahead and do any changes here, this will now be a positive, that will stay positive, this will change the positive, that will stay where it's at, this will change to the positive, and that will stay the same as well. So I went from positive to positive to positive to positive to negative to positive to negative. Okay, so if I look across here, I went from positive to negative to positive, positive to negative. So I went 1, 2, 3 sign changes there. And if I look at the imaginary, okay, the possible zeros I can have is 6 because my degree is 6. Okay, so I can have, well, 3 plus 3 right now, 3 positive and 3 negative already gives me 6, so I could have 0 imaginary, or say I only had 1, okay, 1 positive, because that is less than that number by some even number, because the next even number below that is 2, so 3 minus 2 gives you 1. So what if I had 1 positive 0? Then I could have 3 possible negative zeros, so that would only give me 4, so I need 2 more to make 6, so 2 imaginary. And what if I had, again, 1, because 3 minus 2, that's some even number 2, 3 minus 2 is 1, so what if I have 1 negative, 3 imaginary, I'd still need 2, or 1 negative, 3 positive, I'd still need 2 imaginary zeros. But what if I only had 1 positive, 1 negative 0? That would only give me 2 zeros, but I need a total of 6. So I could even have 4 imaginary if I needed to be. Okay, so remember, you just need a total of whatever degree you have, which was 6 in this case, and go through all your sign flips there. And remember that if you need a negative root, okay, make sure you do your sign flips for any odd number degree or odd number exponent there, okay, because they would need the change in sign for the negative possible root there.